And I'm live. That is pretty cool. And shit, there was a lag for a second there. It still is. So yeah, today is 18th of November 2025, Tuesday. And with that, let's just begin. Go and memory management in Go. And there are some classic things or like some general memory management concepts, and memory management is just getting space from the heap and then reallocating it back or deallocating it back so that the operating system can give that those things back to the yeah, we can take that memory which we are not using and give it back to us or whatever program needs it. So we have the heap and we have our program running, program with P, and this asks the OS give me some space. Then the OS goes to the RAM and gives the address of the starting block to the program, and program does stuff in the starting from this location, and in the given specified size the program does stuff, and then the program says that I am done using all of these things and take that away from me. So yeah, that thing which was being used earlier is now gone and can be allocated back or given to something else. So that is cool. And that is the whole memory management. And yeah, in Go, there is a make function. Let's look at the make function. Whenever we give something to this make function, the first thing is the type, and then the second thing is the count. And yeah, that is what this make function does. This make function gives us stuff on the heap of this type, and this type is specifying how much each cell is going to be. If this type is an integer, then each cell in the memory that we are getting is of 4 bytes in size. So this first thing, which is the type, tells us the size of each cell, and then the size, which is like how many cells there are. If we want 4 integers, we can just say 4 and here integer, and we will get an array sort of 4 integers. So that is kind of cool. Hello, shit. Shit. Hello, first person here. And yeah, that is it. Memory management and make function. The thing about these other languages is that they do not have very good documentation, or I have not been able to find them. Like if you look for Go in C++, there is the main book, the C++ programming language, and you can read that book and you will understand everything, what is going on, what the compiler is doing, and what the functions do. But in tutorials for other languages, yeah, they abstract away the detail and just tell us from high level what things are happening, but at a low level we have no idea what is going on. That I don't like. Make Go make function. New versus make. Okay, let's see. We will use ChatGPT. Yes. How to get uh, storage on the heap. Or yes, let's see what are the built-in data structures in Go. That is a good question, I think. What are the built-in data structures in Go? Yo. And Go keeps things refreshingly Spartan. It doesn't hand you a zoo of data structures like Python or Java. Instead, it gives you a small, sharp toolkit and expects you to handle the rest yourself or grab a well-tested package. That makes sense. Array. We have arrays, a fixed size continuous block of elements like this. We want 5 of integers or we want 10 of integers. Makes sense. Different. This and this are of different types. Shared size is a part of the type. Okay, that is crazy. Useful when you want predicated memory layout and no resizing. Like a child starting at a Lego block. This brick is 4 studs long. Studs, yes. It will be 4 respected. Okay, makes sense. Okay, so there is an array. Makes sense. That is cool. There is an array in Go. Yeah, normal array whose size does not change. But where do we have it? We'll look at it later. And then there are slices, a dynamic view over an underlying array. Think of slice as a smart window. It has pointer, length, and capacity. Pointer, where the slice starts, length, how many elements it sees, and then capacity, how far it can see before hitting the end of the underlying array. And slices are also there in Rust. But let's go, if you want to get into slices, then yeah, we have slices in Boot.Dev, and I think that is a they will give us a better explanation of what slices are. Holidays in college? I mean, not really, but I don't go to college. College doesn't look good. And arrays are fixed size groups. Arrays in Go, slices. Makes sense. Okay, slices. Arrays are fixed sized groups of variables of same type. Classic definition. For example, 4 string is a array of 4 values of type string. To declare an array of 10 integers, we just do this 10. Or to declare an initialized literal, we say 6, and these are the 6 values. Makes sense. And assignment, whatever it is. Okay, this makes sense. Okay. We can declare like this and declare and initialize like this. Makes sense. Slices in Go, 99 out of 100 you will use a slice instead of an array when working with ordered lists. Okay, arrays are fixed in size. Once you make an array like 10, you cannot add an 11th element. A slice is a dynamically sized flexible view of the elements of an array. The zero value of a slice is nil. Okay, so slice is a window inside to an array, and if there are no elements in that slice, that is we are our length of the slice is 0, then it is nil, I guess. Non-nil slices always have an underlying array, though it is always specified explicitly. To explicitly create a slice on the top of an array, we can do this. Okay, we have our array, and then we are saying my slice is a slice of primes from 1 to 4. 1 is 3 and 4 is 2, 3, 4, and the last 4 element is not included. Okay, the syntax is this: lower index, higher index, lower index till the end, this higher index till the end, or the whole thing. Okay, where lower index is inclusive and higher index is exclusive. Both can be omitted to make a slice of the entire array. That also makes sense. I really feel motivated to see how you showed up today. Thank you. Thank you. I mean, yeah, it does get difficult at times, but yeah. And shit, we have a video now. Let's see.
We have way too many names for ordered lists of things in programming. In JavaScript, we call them arrays. In Python, we call them lists. And well, in Go, there are actually 2 unique types: arrays and slices, and they are very different. Arrays are fixed in size, means their size can't change. And we could create a new array of 5 items with this syntax. And then we can assign values directly into each index like this. But this array will always have exactly 5 elements in it. So you might wonder, how is that even useful if I can't add or remove things from the array? And well, frankly, it's usually not. And that's why as a developer in Go, you'll use slices instead, at least like 99% of the time. At least slices are what you'll use directly. See, dynamic slices are backed by fixed size arrays. Slices are just much easier to work with. And here's how you create a new slice. Notice that there isn't a size limit. A slice is dynamically sized. It's a flexible view into a backing array. Now, while you won't often use arrays directly, unless you really don't need resizing, slices do rely on arrays behind the scenes. Aside from being resizable, slices are, as the name suggests, slices, or parts, of an array. You can use slicing syntax to create a new slice that just has a section of an existing array or slice. For example, say we wanted to get the second through the fourth items. We can create a new slice like this. The first index, 1, is inclusive, and the second 4 is exclusive. Now, slices in array in Go are stored in contiguous memory, just like arrays in C, because accessing data stored contiguously is faster than pulling it from a bunch of different scattered memory locations. The downside of contiguous memory is that we can't expand a slice in place if there's no room. Say our slice uses memory addresses 700, 701, and 702. If address 703 already holds some other variable, we can't just expand into it. And that's why backing arrays are fixed in size. It prevents us from overwriting other memory. So how do slices grow? Well, they need to automatically allocate a new, larger backing array and copy the data from the old array into the new one. For example, let's say we have this slice with 3 elements. If we append a new value, 2, then a new array, say of length 6, is actually created automatically for us. The old values are copied into it, and then the new value is just added. This new array lives in a completely new memory location, but the same slice that we had originally still now points to it. Now, this whole copy operation, where we go from the old array to the new array, might sound slow, and sometimes it is, but Go is smart. It doesn't grow the array for every single new append. Instead, it allocates extra space ahead of time, so resizing only needs to happen every so often.
That is cool. Slices and similar stuff. What are you working towards? What you want to achieve? Maybe become financially independent would be one of the first things I want to have. And then become a scientist. Yes, physicist. Hello, bro. What are you trying to do? This ain't code forces. Yes, this ain't code forces. We are learning Go here and how memory management works in Go. And we have 2 things. We have slices, data structures in Go. We have a normal array with whose size is fixed. Okay, like a normal C array, but this array is on the heap instead of being on the stack, which happens in C. And then there is slices. Slices are sections of a array which exists in the heap, and slices can grow in size or decrease in size, so slices are cool. And then we have maps and strings and struct and what the hell, we have channel somehow. Okay, we will look at it later. But yeah, we have arrays and slices. I think that is cool. That is cool. That is cool. We can move forward with slices. We watched the video by Lane Wagner, and slices wrap arrays to give a more general, powerful, and convenient interface to sequences of data. Slices wrap arrays to make sense. Okay, slices wrap arrays to give a more general, powerful, and convenient interface. Convenient, yes, this is very convenient because slices can change their sizes. So yeah, that is quite convenient, I would say. And 2 sequences of data. Sequences of data, data that appears in sequences. Cool. Sequences of data. Except for items with explicit dimensions, such as transformation matrices. Most array programming in Go is done with slices rather than simply arrays. Okay, so okay, that makes sense. That does make sense. So we have, what do we have? We have slices, and these slices, they don't really have any data. They don't really have any data themselves. There are on the heap or memory, yeah, on the heap. the whole heap is divided into memory locations, and on the heap we have some normal arrays, and a slice just points to a section of the array, and that is cool. That is cool. Why? Because um, let's say this array has some 10 elements, and we can access all of those elements through this slice, and then we want to add a 11th element. But if we were working directly with the array, we cannot expand the array by one more. So but the slices syntax, if we append one more element to the slices, the underlying mechanism in Go will handle all of this. The underlying mechanism in Go for slices, it will create a new array, and this will copy all the data from the old array into the new array, and this new array will have about double the size as the original array, and the 11th element will go at the new location, whatever it was. So that is cool. That is cool. Yo, how's everything going on? Yo, we got slices. We got sliced. And okay, that is actually cool. That is actually cool. And what is the syntax to add stuff in the slice? I guess this didn't work yesterday in Code Forces. I think there is some like underlying mechanism about how printf and scanf work in Go. And this is what I do not like about other languages. In C++, we have the book, the C++ programming languages, and it explains everything in detail, how things are happening under the hood, as if we are an adult. But other books for languages, they don't do that, or like their basic documentation, it doesn't explain things in low level details. They just, yeah, they explain things from a high level abstracted point of view. And yes, cf ls cd bootdev ls, yeah, I mean go. Okay, how do we create a slice? We create a slice. My slice will be equal to integer, and it is empty. Okay, then we will do for I equals 0, I smaller than equal to 10, I plus plus, I equals 0, I smaller than 10, I plus plus. Okay, I plus plus, fmt, and we will say int, shit, that is not how, c equals 0, and then fmt dot scanf digit comma c, get into c and append. That is what we need. Append to my slice c, and that will append things to our slice. Yes, how do we, yeah, how to loop in a range like Go? Because what do they mean by this thing can be modernized using ranges? Let's see, but not including. We can explicitly write, that is not very good though. Strings, yeah, that is what we need. Uh-huh. I have a for I equals 0, I smaller than 10, I plus plus loop. But the LSV says that it can be modernized. How do I do that? For I in range 10. Okay, shit. That is actually pretty cool. For I in range 10. Okay, but want to use I, then what? If I don't want to use I, then what? I is declared not use for range 10. Shit, that is even better. That is very cool. Explicitly or this for range 10. But what is the range function doing and what is it doing? Then for I range in my slice. What it do is fmp dot print this number with a space. Yeah, print this number with a space, or can we do the same syntax that we use? Print is print I and then or new space depending on, yes, there is no ternary operator, so yeah, um, print I a space and then fmt or print new line. Go run dot and okay, shit, it is asking for number. 1 2 3 4 5. Shit, yes, because we are iterating through the index. We do not want to iterate through the index. It is very dumb. Go run dot and it is asking for numbers. Shit, I messed up in that one thing. Okay, 12. After 12, we read 0 for R. And then it went out the right way. Okay, that is nice. That at least does work. So okay, that is like how do we do work with slices. That is cool. That is cool. Okay, moving forward. Slices hold references to an underlying array, and if you assign one slice to another, both refer to the same array. Okay, so that is cool. That is cool. That is cool. So here, if we do main dot go, and after filling our slice, we do my new slice equals my slice declared and not used. At this point, my new slice is also pointing to the same array that my slice is pointing to. So that is kind of cool. That is kind of cool. Yeah, that is kind of cool. If a function takes a slice argument, any change it makes to the okay, we will not read what it says. We will actually see what happens. We will have a function. We will call it update slice, and as its argument it takes x. What is x? X is a slice of integers, and this thing doesn't return anything. And what happens is for x, for c equals range in x, we'll do C multiply by equal to 2. We are updating every number and making it equal to 2. Twice its original value. And here before printing, we call the update slice on my slice. Let's see what happens. What are the bits? What will happen? I think the original slice will get updated. Here this function is asking for a slice. I don't think slices are implicitly copied. They might actually be implicitly copied. I don't know. And here we are passing our slice after giving it inputs. Let's make this range 5. Okay. Go run dot, and it is asking for numbers 1, 2, 3, 4, 5. Okay, the values didn't change, so a copy is being sent. How can we change that behavior? I think if we say we have a pointer missing comma in the list, that might work. I think now x is a pointer to an slice. X is a pointer to a slice. I don't know how pointers work in Go, but that is the hypothesis. X is a pointer to a slice. And then we are going to the array, to the slice that is pointed to by X, and then at that location we are updating C, the value. So, okay. Okay, and here we are sending a pointer. Go run dot 1, 2, 3, 4, 5. It didn't update. Shit. It didn't update. Shit, that is like actually kind of bad. Slices hold references to underlying arguments. If a function takes a slice argument, yeah, yes. If a function takes a slice argument, any changes it makes to the elements of the slice will be visible to the caller and are analogous to passing a pointer. We will cover pointers later to the underlying array. A read function can therefore accept a slice argument rather than a pointer and a count. The length within the slice sets an upper limit to how much data to read. Here is the signature of read method of file type in OS package. Read takes in a buffer, returns n number and error on the file method. This is very cool. This is very cool. This syntax is very easy to read, kind of easy to read. Which references the other slices reference the arrays. Yes, slices reference the array, not the other way around. And multiple slices can point to the same array. Yes, they can point to the same array. A function that only has access to a slice can modify the elements of the underlying array. Yes, true. It is true. And before moving, okay, yes, we do have the make function. Make function is a nice function, but why are we unable to change the element here? C equals C into 2. C equals C 2. Let's say this, and then xi multiply by equal to 2. What happens now? Go run dot and 1, 2, 3, 4, 5, and it does get updated. So the problem was in this part when we were doing C, that is get the value also in this range. We are not getting a reference to that value, we are getting a copy. So if we change C here and say C becomes twice we are not actually doing anything. Now let us do elements and go using range. Okay. P is modify the structure. But get reference. Yes, that is the exact question we want to answer. Let's see. And what do people say? Range I. Okay, shit, that is the only way. We will have to explicitly say that we want a slice. Or is there any other? No, there doesn't seem to be any other way in the last 14 years. Okay. Uh, Here, 1, 2, 3, I and C equals a reference to xi and C multiply equal to 2. That is a crazy syntax. Go run this thing and 1, 2, 3, 4, 5, 2, 4, 6, 8, 10. Yeah. Okay, that's cool. That's cool. Slices. Now make most of the time we don't need to think about the underlying array of a slice. Okay, we can create a new slice using the make function. Make a slice like this. Make a slice like this. Okay, a few questions. First of all, about this thing. When we do this, then do we get a slice on the heap or on the stack? Where are we getting the slice on? Okay, depends actually. Okay. Um, Go allocates an array holding the actual data like this. Okay, and a slice header holding pointer to element 0, length and the capacity. Where is the array located? Makes sense. This is decided by the escape analysis the compiler performs. If the data does not escape the function, the array lives on the stack. If the data does not escape the function, the array lives on the stack. Okay, shit, that is cool. Escape analysis. Escape analysis. That is something. The array lives on the stack. S is a slice and okay. The compiler sees that S never leaves F. In this case, the underlying array will be allocated on the stack. Okay. Okay, that is cool. So the compiler is seeing how things are going to go when the program runs. That is some high level prediction stuff, I would say. If the slice escapes the function, the array is moved to the heap. Okay. And now S must live after the function returns. Stack memory dies with the function. So Go moves the backing array to the heap. Okay. Where is the slice header allocated? The slice must be on the stack. Smallest structure, only 24 bytes. If the slice does not escape, the header stays on the stack. If the slice escapes, the header also escapes and moves to the heap. Moves to the heap, not that it was on the heap in the first place. The trick, composite literals can go on stack or heap. Composite literals can go on stack or heap. That is something is not automatically a heap allocation. This is not automatically a heap allocation. How to check escape analysis ourselves and stuff like that. Bottom line, okay, we do not explicitly know where it goes. Okay, that is something. Then what is a make function for? Most of the time we don't need to think about the underlying array of a slice. We create a new slice using the make function like this. Here we are creating a slice of integers and 5 and 10. Okay, shit. Length of the slice and the capacity. That is actually cool. That is actually cool. We need a slice of size 5, but we want the underlying array to have a size of 10. The capacity argument is usually omitted and defaults to the length. Okay. Slice creates slices created with make will be filled with the zero value of type, zero value of the type. And by zero value they just mean the default value. If integer, then 0, and if float, then 0.0 or stuff like that, zero value. If you want to create a slice with a specific set of values, we can use a slice literal, like this, but we are not using the make function with this. If we want to create a slice, will be filled with zero value. Okay. If you want to create a slice with this specific set of values, we can use a slice literal. Slice literal. This is what a slice literal is. Okay. Notice the square brackets do not have a 3 in them. If they did, you would have an array instead of slice. Makes sense. Length. The length of a slice is simply the number of elements it contains. It is accessed using the built-in length function. Call the length function on my slice. Makes sense. Capacity tells how many more elements or what is the size of the underlying array to which the slice is pointing to. The capacity of a slice is the number of elements in the underlying array counting from the first element in the slice. It is accessed using the built-in capacity function. Generally speaking, unless you are hyper optimizing the memory of your program, you do not need to worry about the capacity of a slice because it will automatically grow as needed. Yes, yes, that is also the same thing that happens in C++. Either we can beforehand tell the capacity using the not resize reserve function in C++. We can say that this vector is going to use some specific amount of storage. So yeah, keep that much storage in the heap, and yeah. And then indexing, a programming concept you should already be familiar with. By indexing array indexing, you can access or assign a single element of the array or slice by using its index. Yes, this is a slice. Get the second element of the slice, put the 0th element equal to this, and now the slice is this. We can print the whole slice. That is actually pretty cool. So we didn't have to do this thing here. We could have just said print ln my slice, and this would work. 1 2 3 4 5, and yeah, it does work. Assignment, whatever the assignment is. Okay, this all makes sense. We have the make function which creates a slice. Okay, and does the make function always create a slice on here? Function always slice on the heap. Does it always create a slice on the heap? That is a good short answer. No. Shit. So Go is optimizing quite a bit, I would say. Go is optimizing quite a bit. Let's dissect this properly so you know the ground reality, not the myth. This thing creates a slice. Okay, 3 pointers, length, capacity, and a backing array. The question is, where does that backing array live? Yes, heap, sometimes stack, also very often. So most of the things are on the stack in Go. Okay, that is different from how things happen in other languages, because in C++, whenever we declare a data structure whose underlying data is supposed to go on the heap, it always goes on the heap. There are no conditional things. The handler of the data, that the handler, it stays on the stack and smoke, stack, and the underlying data that the handler is pointing to and goes to the heap. And yeah, in C++ we call heap the free store. FS, file system. Nope, free store. Okay. When make allocates, but on Go, the things are different. In Go, when we declare something, we don't know whether it will be stored on the heap or on the stack. The Go compiler goes through the whole thing and decides where to store the thing to optimize the stuff. Okay, the question is, where does the thing go? Heap, stack, we don't know. Goes escape analysis decides. Okay. Goes escape analysis in Go by Pranay Kundu. Okay, let's go. When make allocates on the stack, if the compiler can prove the slice does not escape the current function, that is, it never needs to live longer than the function call, then backing array is stored on the stack. In this case, yeah, s is always inside this function foo, so it is on the stack. When make allocates, not making, when make allocates on the heap, if the slice escapes the function, meaning it must continue to exist after the function returns, the backing array goes on the heap. Like here, we create s inside foo, but then we return s. So it lives on the heap. Global append. We have a global two-dimensional vector, a two-dimensional slice of bytes called global. And inside foo, we make b, which is a byte, which is a vector of bytes, size this, and we are appending to global this b thing. Okay. Okay. So this will be on the heap. This will be on the heap. This b will be on the heap. That is very genius. Ken Thompson is genius. How to know where it actually is allocated? We can use this GC flags. Example output would be this does not escape. Shit. Let's use this -GC go compiler flags M. What is M? M must be like memory management or something. And this thing is called escape analysis. Okay, we will read this article in a while, in a minute, after doing our own experimentation. So go build GC go compiler flags equals M, and the file is main.go. Yo, we have some stuff. Can inline update slice. Command line arguments. Can inline update slice. We can make update slice inline. Inlining call to this function. Inlining call to this. Inlining call to this. X does not escape. X does not escape makes sense. Yes, that is true. Moved to heap. C. C is moved to heap. C is moved to heap. C is moved to heap. So there must be some rationale behind it. This escapes to heap. Escapes to heap. Okay. Okay, this escapes to heap. And okay, these things, I don't know why these are escaping to heap. They are happening because of whatever the escape analysis does, analyzes. Argument does not escape, append. Let's see. Out of Go lang. How to Go assembler. Go tool compile S main. Go to compile S main.go main.s. Shit, we got some error. We got some error. Compile S. Yes, everything was cool. We do have main.s and could not import fmt. File not found. Could not import fmt. Let's write a simple Go function then without fmt and stuff. We won't be able to scan, that is completely fine. We create a this thing here, and 1 2 3 4 5. There are 5 things in this. Println my slides. Go to compile s main.go, save it in main.s. That does seem to be working, and that is some strange assembly language I have not seen. And this is assembly because we have instructions here. I guess the assembly part starts from here. The assembly part starts from here, and all of that is just, I don't know what this thing on the left means, but yeah, the main assembly part is here. Text main, yes. We also have some alignment stuff. I think share. Okay, I think does Go uses LLVM. This might be, no, does not use LLVM. It uses its own compiler, which was designed for fast compile speeds. However, there are alternatives. LLVM based this Go LLVM, LLGo. Okay, Go has its own compiler. Why does Go not use LLVM? Because it wants to achieve high fast compilation times. I thought this might be a intermediate representation which will go to LLVM, but no. And this is some kind of assembly language, which is not the point. We not go. Yeah, we cool. We cool. The scope depends. Scope depends. Let's see. Understanding, analysis, Go built-in data structures. Okay, the compiler runs a thing called escape analysis, which goes through the code and sees if there is something which is used in the function, and that thing always remains in the scope of that function, then that thing will be stored on the stack, otherwise it will be stored on the heap. So that's cool. Let's see how this works. Go uses escape analysis to determine the dynamic size of Go values. Typically, Go tries to store all the Go values in the function stack frame. Okay, the Go compiler can predetermine which memory needs to be freed and emits machine instructions to clean it up. This way, it becomes easy to clean up memory without the intervention of Go garbage collector. That makes even more sense, because there they have a bias towards storing things on the stack, because if they do not, if most of the things are on the stack, then there is no need for the garbage collector to run. But if there are some things on the heap, only then the garbage collector will run. This way of allocating memory is typically called stack allocation. Okay, so they have a bias towards storing stuff on the stack, because if the stuff is on the stack and nothing is on the heap, then there is no need for the garbage collector to run. But when the compiler cannot determine the lifetime of a Go value, it escapes to the heap. A value may also escape to the heap when the compiler does not know the size of the variable. Because makes sense. If Go does not know the size of the variable, then it will go in the heap, because we can change the size later. So it is too large to fit, or it is too large to fit on the stack. Or if the compiler cannot determine whether the variable is used after the function ends, or the function stack frame is not used anymore. Okay, so we have our basic classic stack. And then we also have heap, makes sense. And there is the escape analyzer. Escape analyzer. And escape analyzer looks at each variable which is used wherever it is used, and if what are the things that go on the stack. Variables not too big, variables not escaping the scope of the function, variables which are not too big, which are not escaping the scope of the current function that they are used in. That is quite it. That those are the variables which are on the stack. So, and here variables with undetermined size, variables which are too big, variables which have a undetermined size, variables which are too big, undetermined size, variables which are too big, or variables which escape the scope of the which escape the stack frame. And yes, that would be nice. Yes, that is it. Those are all the things which come on the heap, which are stored on the heap, and these are all the things which are stored on the stack. And then also there is a bias to store to store data on the stack because go garbage collector doesn't have to run. That makes sense. That does make sense. That does make sense. That does make sense actually. Blue, green, yep. That is cool. Okay. Let's read the rest of the article. But when the compiler cannot determine the lifetime of a Go value, it escapes to the heap. A value may also escape to the heap when the compiler doesn't know the size of the variable, or it is too large to fit on the stack, or the compiler cannot determine whether the variable is used after the function ends, or the function stack is not used anymore. So in case of confusion, or in case of clear knowledge that this current value is going to escape the current function, then we store things on the heap. The compiler does, not us. Even said so, can we truly and completely know whether the value is stored on the heap or the stack? The answer is no. Only the compiler would know where exactly the value is stored all the time. As mentioned in this doc, the Go language takes responsibility for arranging the storage of Go values. In most cases, a Go developer need not care about whether these values are stored or why, if at all. Okay, we don't need to care whether the values are on the stack or on the heap. And this is an article by Go, a guide to Go garbage collector. That is nice. I guess you can also go through this at some point. Okay, that is nice. There might still be scenarios where we might want to know the allocation to improve performance, as we know physical memory is finite and overuse of it might result in unnecessary performance issues. Let's now see how we can determine when and why a variable escapes to the heap. When and why a variable might escape to the heap. We will use the go build command to determine it. Run go build to get various options for a go build. We will use this thing command to ask the compiler where the variables are being put. Let us now go through this example. What do we have here? We have our main function x. It has a value of 2 and x is being passed to a function called square. Square takes in a variable x and x square takes a copy and return this, and that return value is not being handled here. When we run the above go build this command, we get this result: can inline square, can inline main. Inlining is called to square. Right now everything is in the stack frame because this value which is returned by this function is not being handled by x, and even though these are integers. Okay, let's now modify our code to return a pointer to from the square value function y and return pointer to y, pointer address of y. When we build this, we discover inline is moved to heap. Why we moved y to heap? Because a reference to y was being returned. Even though it is not being handled here, the pointer is returned. Here the value y escapes to the heap. Now notice why this happened. Some advertisement. The value of y has to prevail once the square function life cycle has finished, and hence it escapes to the heap. Yes, we might use the same variable y later on outside the scope of this function square, therefore y goes to the heap. Let's modify the above function. Okay, let's see. I think here nothing would go to the heap. In this code, nothing should go to the heap because x stays in the main scope. Even when this function square is called, this takes in a pointer. Shit, no, this will be on the heap because when this function is square function is called, it will create a new stack frame, and it will create a new stack frame, but I guess maybe this pointer can have a value on the stack itself. Let's see. Let's modify the above function. Let's make, yeah, but the hypothesis is that x will not move on the heap. X will stay on the stack. Hello, when I joined, you were talking about heap. I went away for 45 minutes or so. You're still talking about heap. Shit. Oh, what are you even doing? We are seeing about heap. We are talking about heap, I guess. Yes, in Go, this is strange. The developer does not need to know where the variable is going to be stored. The variable can go on the heap or on the stack. There is a thing called escape analyzer, which goes through the Go code and figures out if the variable is not too big, variable is not escaping the scope of the function in which it was created. That is, the variable is not being returned outside, then that variable, no matter if it is an array or whatever, it will be on the stack. And otherwise, if the compiler cannot figure out the lifetime of a variable, if the variable is too big or the variable leaves the scope of the current stack frame, that is, the variable is being returned by the function, then it will go on the heap. And there is a bias. By default, the compiler will try to put things on the stack, because if things are on the stack, then the Go garbage collector doesn't have to run. So that is kind of new, novel idea, because in C++, we are very aware where the thing is going. Whether we are on the heap or not. But here we don't have to care. That is kind of convenient. And yes, here, look at this. Here we have x. x is created in main. X is an integer and we are sending a pointer to x to this function square. Even so, x is passed on to another function. X is still in the scope of main because the stack frame for this function square will be will be will form on top of the main function, or to be like technically correct, at the bottom of the main function, because stack grows downwards and then there x is being accessed. So x could point to the variable in the stack. I think that x will be stored on the stack and not on the heap. Let's see. Let's make our square function accept a pointer and not return a value. Let's see. I think it will go on the stack. X does not escape. Let's go. Let's go. X does not escape, so it will go on the heap. Crazy. When we build the above code, we get can inline square main inlining call to square. X does not escape. Yes, X stays on the heap, so that's cool. I like this design more because I know many people who don't know shit about this and would cause all sorts of problems. So language handle it. Yeah, like Python. That is why Python is kind of convenient and easy. But even but the thing is, this abstraction should be like not hidden. Right? There should be an option for someone who wants to tinker, which should give them the ability to tinker, like the Steam Deck. And yeah, that is why I do not like Python. Python is cool, but I do not like it because I do not know what is happening. And same with JavaScript. I do not know what is happening under the hood. When I declare something or do something with it, I don't know what is going to happen. But with C++, I almost know exactly what is going to happen. Where the thing is, stack, frame, static memory, where, and yeah, that knowledge is like very cool. The control is cool. Notice in the above function, even though we are passing the pointer to the square, the compiler mentions that the variable x does not escape. This is because the variable x is created in the main function stack frame, which lives longer than the square function stack frame. Yes. Let's make one more modification to the code. Let's make our square function do something. Okay, y will be on the heap. Y will be on the heap. Y is an integer and we are returning pointer to the integer. So y will be on the heap. X will be on the stack and y will be on the heap. So moved y to heap and x does not escape. Let's go. Now notice carefully, the result of this code is a combination of examples 2 and 3. If we look even further closely, we can say that sharing memory down from the main to another function typically stays on the stack, and sharing memory up from a function to the main function typically escapes to the heap. Makes sense? That is what we are seeing. Y is escaping, which was called in a lower level function and returned to the higher level function, the main function. Okay, we can never be completely sure about it always, because because only the compiler would truly know where the value is stored, but this still gives some hint when an escape to the heap may occur. Cool. In conclusion, okay, let's conclude this. Escape may escape analysis in Go is a way. So and Go module and the like the borrow checker, is it like a part of the compiler? It must be a part of the compiler, but just guide to escape analysis. Okay, we can or just read this article on Go garbage collector, because and I'm focusing more on this thing, Go garbage collector and memory management, because this is one of the things that I have to do for my assignment. I have an assignment and this is one of the things I have to do. Memory limit. Shit, they have a slider. Shit. GSOC. that is something, that is something. Okay, not now, not now. Let's play around some more. Okay, what do we know? We know escape analyzer. Shit, this looks very beautiful. Okay, we know that there is a thing called escape analyzer. We know there is a thing called escape analyzer which does analysis and decides to put stuff whether on the stack or on the heap. And that is cool. Right. And we have slices. About yes, about the data structure part. We have slices which have a underlying array. We have slices which have an underlying array to which it points to, and that is kind of it. And this underlying array can go on the heap or on the stack depending on what the escape analyzer decides to do. And the developer doesn't need to care unless they are like John Conway or someone. Yes, I wanted to say John Carmack. Yes, cool. Makes something, whether on the heap or on the stack, depends. Make says, give me this type, this many things of this type, and keep the capacity to be equal to this. So the size of the slice would be this, but the underlying capacity of the array to which the slice is pointing to would be the second argument. Cool. And length and cap review. Due to some reason, the length of a slice may change as long as it fits within the limits of the underlying array. Just assign it to a slice of itself. The capacity of a slice inaccessible by the built-in cap reports the maximum length the slice may assume. Let's do this. Let's actually do this. We will say that we need a slice of integers. We will use the make function. Make, give me a slice of integers and make the slice have one element and make the capacity equal to 2. And then we will keep going for range 10, let's say. Yeah, for range 10, we will say c equals 0 and fmt dot scanf a digit into c, and 0, and then we'll say my slice equals append to my slice c, and yes, append to my slice c, and then also print ln capacity of my slice. We will see how the underlying capacity of this thing is changing. Print ln my ln degenerate go run dot. It is asking for input 1, capacity is 2, capacity is 2, or we can write this a little bit more leanly. Enter number, and here say go run this. Enter number 1, capacity is 2. Enter number 2, capacity is still 2. Enter 3, capacity increased to twice the earlier value. Now it is 4. 4, capacity is 4, we have entered 4 numbers. Now the capacity is 8. That is crazy. Shit, we do not have, we can also do this in C++. This looks cool. Now 16. That is cool. Capacity is becoming twice the last value of the capacity. That is cool. That is cool. Let's go even higher. Let's say, okay, what I want is capacities to be yeah, capacity is our slice. It is not declared, does not matter. Int c or set let's c equals 2 and capacities equals append capacities dot c, and then here we don't want to rewrite. We'll say d, enter number d, and don't print this, and yes, take this, and yes, also append to my slice, and if current capacity of my slice is greater than the last capacity, then c equals the new capacity of my slice, and also capacity equals pen to capacities c, and in the end print line capacities, and that is cool. This should work unless we remove this. Okay, go run dot and 1 2 3 4 5 6 14 15 16 17 18 19 20, and yo, the capacity was 2, then it became 4, then 8 16 32, and that is cool. That is kind of cool. We can see how the capacity is changing. The length of a slice may change as long as it fits within the limits of the underlying array. Okay, just assign it to a slice of itself. Just assign it to a slice of itself. The capacity of a slice accessible by the built-in function cap capacity reports the maximum length the slice may assume if we keep it bounded to the underlying array that we are working with. Here is a function to append data to a slice. If the data exceeds the capacity, the slice is reallocated. The resulting slice is returned. The function uses the fact that length and cap are legal when applied to the nil slice and return 0. Okay, this function append takes the slice and the thing that you want to append and returns bytes. Okay, L is the length, effective go, referenced from effective go. Effective go is this thing. Okay, documentation, installing package documentation, command line documentation, uh, how to write go code, a tour of go, and okay, it does have nice cool documentation, it seems. How to write go, Write a tool documentation page for a set of in-depth articles. But where are the in-depth articles? Developing modules, getting started, tutorial, get started, tutorial, create a module, tutorial, getting started with multiple module workspace, tutorial, developing a RESTful API with Go and Gin, tutorial, getting started with generics, tutorial, getting started with fuzzing, writing web application, how to write Go, effective Go, frequent FAQ, editors, plugin, diagnostics, garbage collector. Is there a article on Go memory model? Wait, this would be nice. This would be nice to read. Yeah, we'll read this article after we get done with slices. And also after slices, I also want to do maps. So yeah, we'll also do maps after this, like today. Reports the maximum size, and okay, what we are doing, we are taking in the length, and if L plus length of data, the stuff that you want to append, if that thing is greater than the capacity, then we need to reallocate. We make a new thing where the length is twice the current length, twice the required size. The copy function is pre-declared and works for any slice type. Copy onto new slice data from this slice, then slice equals new slice, and then add things. Slice equals slice 0 to this, and then copy from the last point to the current point. Slice 0 to L. Yes, L plus length of the data. Yes, okay, that is cool. In this part, we are increasing or adjusting the size of the slice to be equal to the size that is required right now. The original length of the size plus the length of the data that we are appending. That is cool. We can write our own implementation of this thing. Function append. This takes in, and we our slice. This is a slice of integers, right? And slice of integers, and data is bytes, and this returns bytes, undefined bytes. Byte is the way to go. And then we take in the length, slice dot length of slice, declared L is not used. If capacity of slice is smaller than L, the data in the slice already present, plus the length of the data that you want to add, then we need more data here. Then new slice will be equal to slice, will be equal to make a new slice. Will make a new slice whose capacity would be twice the currently required range. The currently required range is L plus length of data. And then we will copy onto new slice the original slice, and slice equals new slice. That is nice. And now we want to resize the slice. Slice equals slice from the beginning till L plus length of data, and then copy on from beginning from L till the end. Yes, beginning from L till the end. Copy what? Copy data. Hmm. Integer. This slice is both are of type byte. Okay, makes sense. Substitute end with. Who said bytes? Shit. Substitute end with a byte, and we can use the same byte there. Okay, and copy what? From L till the end, and return slice. And instead of make this, we can do this. And here, instead of append, we will use append. What is C? C is not a byte. Share. Okay, yeah, I mean, we can work with that. We can work with that. And we can fix C to be a array of bytes and everything in the middle. Assignment exactly, you need to make a garbage. No, I do not need to make a garbage collector. I have to study how memory management works in Go and in Rust, and yeah, make a PPT and stuff. Go's documentation is quite good. Yes, it seems to be. I hadn't read this stuff. And this is cool. This is something that I want to read. And then there's this guide to Go garbage collector documentation. Where Go values live, tracing garbage collection, Go GC, Go garbage collector. Memory limit, we have latency, Linux, transparent, huge pages, THP, Uma Thurman. Okay, that is cool. And what is the cap function written? It returns the capacity of the underlying or the size of the underlying array. Shit, this thing is. What does the length function do? It gives us the size of the current slice or the array. What do len and cap do when a slice is nil, return 0? Panic. No, they return 0. And Vedic, variadic. Okay. Many functions, especially those in the standard library, can make an arbitrary number of final can take an arbitrary number of final arguments. This is accomplished by using a dot dot dot, 3 dots. In Lua we use 2 dots, I think. Syntax in the function signature. Variadic makes sense. A variadic function receives the variadic argument as a slice. Variadic makes sense. Variadic. A function that can accept a variable number of arguments. Printf is variadic. Min in C is variadic. Okay, functions that can take any number of input arguments are called variadic functions. Okay. A variadic function receives the variadic arguments as a slice. This is a function that takes strs, which is a slice of strings, and returns a single string final. Strs is just a slice of strings. So why don't we write a slice? We do not write it as a slice because it makes sense. I guess then if we make this thing byte and we make this thing, then shit, I thought this might check out, but it does not check out. If we say 0 and 1, then it checks out. That is cool. That is cool. Now it is a byte. Now, yeah, now this thing is a byte, and that is cool. Okay. Let's change our thinking. my slice, and my slice equals append to my slice a bunch of things. Append 1, and then append 2, append 3, append 4, and we can like call this again and again. Could convert argument to string. That is completely okay. Yo, that is correct. That is correct because we are getting the numerical value of these things. And if we were to do my slice equals append to my, I do know the character code of some things. A new line is 10 and small a should be 97, I think. Go run dot 10 and 97. Cool, let's go. So yeah, we are getting stuff. Okay, you can look for Discord Go memory spike graph and add it to your project. It may help. Shit. Shit. That is cool. I'm getting peer reviewed. It shows the spike where whenever Go garbage collector is ran. That is cool. CPU system. Okay, whenever the garbage collector runs, the CPU system goes up. Average response time increases. Response time maximum mention is something. I guess that makes sense. Online members. Okay, this is not even related to the thing we are looking up. Okay, someone's Discord is taking 97% of their RAM. That is messed up. Should right go or is this or written in Go electron from Go to Rust. No, Discord's code is not written in Go as it switched the critical read states service from Go to Rust. Around 2020, shit, COVID, due to performance issues caused by Go's garbage collector. And these were the performance issues. Go's garbage collector. The first article might be helpful. The rest graphs are something else. Yes, they were crazy. This article, Go memory model. Okay, so this problem is with Discord, but this problem would arise with anything, any big thing which is running Go, and in that case, every big software would try to switch from Go. So, what were the use cases that the creators of Go, Mr. Ken Thompson, had in mind for Go? Garbage collector. I guess their target audience was people who don't want to bother with the memory. I recently created a code sandbox using Go. Okay, shit, bro created a sandbox, kind of copied the Docker's way, but mine is way faster in terms of startup time, and also size is around 2 MBs using Alpine Linux minimal file system. Okay, shit, that is cool. That is cool. That is cool. I don't know how Docker works, but that is actually cool. Discord deals on such a huge scale, I won't be surprised if they switched to writing raw assembly shit. David Goggins. Go would run pretty smooth for 90% of the time, but Discord is just on whole another level. Okay. Uh, how much is the Go main thread running in the compared to the garbage collector, how much is the main stuff running? Allocation rate, okay. The proportion of time the given main thread runs compared to the garbage collector is not fixed. That is just AI. How to choose the best Java garbage collector? Don't collect my garbage. So people are facing problem, it seems, with the Go garbage collector. Concurrency model, it threads are very light because it is made with the specific idea in head that we want to make our language concurrent. Shit. Okay, my camera is actually paused somehow. Yeah, let me try to fix it. Yeah, it just happens sometimes. Last, I read Discord deals billions of messages per second or something. Should billions of messages per second? That is too much crazy. Or was it per day? Seconds would be crazy. Billions, like it would be like 1 in 8 person is actively messaging on Discord every second. So yeah, I guess it would be on day per day basis. Read the first Medium article which showed that graph. It went away. It went away. Go reference. Wait a minute. The camera. Yeah, the camera. Uh, it is not working. It was per second. Bro, per second is too much. Per second is kind of too much. Discord messages. Message rate. Uh, daily or something. Not like that. Uh, no, yes. Daily, not in India, like anywhere. Mm, yeah, per day. So yeah, it is not second. Second was actually quite a bit. Billions of messages per seconds would be quite a bit. And this thing is quite interesting. I recently created a code sandbox using Go. And yes, the camera is broken. And yes, it will stay broken. And this will be a faceless YouTuber. Up to 4 billion per day. Yes. Now I'm like Technoblade, faceless YouTuber. Kind of copied the Docker's way, but mine is way faster. Docker's. Okay, my understanding of Docker is it boots up a very minimal operating system and runs your stuff on that operating system. And I think that is wrong. Yeah, I think that is quite wrong. My understanding is quite wrong. And about the science uses 2 MBs using a Alpine Linux minimal system. That is crazy. You are running another Linux operating system in 2 MBs. Ah, shit. Okay. It's called Go Memory Spike Graph. This thing is called is switching. Shit, they wrote this guy, Jesse Howard from Hogwarts. Let's see what happened. Rust is becoming a first-class language in a variety of domains. At Discord, we have been successful with Rust on the client side and server side. For example, we use it on the client side for our video encoding pipeline. On the client side, okay, so when I run Discord, I have Rust running there. And I mean, Docker wasn't made for running just code. That is the thing, I'm too stupid. I don't know about the functionality of Docker. We will have to make our own Docker for that. And Docker has significantly more features and things. So of course it is slow a bit. Yeah, shit. I guess yeah, that is not a fair comparison. Makes sense. because yes, you're not doing everything. Your Docker is not doing everything. But if you are running a whole operating system, which is the main purpose for Docker, then I guess you are doing quite a bit of work that Docker also does. So of course it will be slow down, but compare it with something individual made which doesn't even have 1% of its features, and saying it is faster. It is a little wrong. I guess that is the main feature that Docker is supposed to do. Run some code in a virtual environment. Yeah, a little wrong. And at Discord, we have been successful. We have seen success with Rust on the client side and server side. That is actually cool. Okay. For example, we use it on the client side for our video encoding pipelines for Go. They have their own video encoding pipelines, okay, for Go live, and on the server side for Elixir, NIF, uh, NFT. Most recently, we drastically improved the performance of a service by switching its implementation from Go to Rust. This post explains why it made sense for us to re-implement the service, how it was done, and the resulting performance improvements. The read state service. That is cool. Bro looks actually like this. 4th February 2020. The read state service. Discord is a product focused company. So we will start with some product context. The service we switched from Go to Rust is a read state service. Its sole purpose is to keep track of which channels and memory you have read, of shit, which channels and messages you have read. Okay, makes sense. The read state is accessed every time you connect to Discord, every time a message is sent, and every time a message is read. In short, read states is in the hot path. We want to make sure Discord feels super snappy all the time. So we need to make sure read state is quick. Okay, so read state tells the client whether we have read a message or not. Alpine Linux is very lightweight distro, so that is a good thing. There was recently a CVE critical error where hackers installed whole as operating system on hypervisor, Hyper-V on Windows. I also watched the low-level video. They installed Alpine Linux because how small and lightweight it was. The main thing I wanted was just a binary. uh, was just run a binary. I actually wanted an online judge OJ only for C++ because making multi-language is something I cannot do. This is a learning project. Yes, this is a learning project. Learning projects are cool. I will also make my own Docker. Don't worry. For this, we need to provide a bare bone, super slim file system. Yep, bare bone. So yeah, learning project. But also, yeah, this point is also pretty nice. Saying that yours is faster is not like total justice to the Docker people, because they are also doing quite a more stuff. Okay, read state is here. With the Go implementation, the read state service was not supporting its product requirements. It was fast most of the time, but every few minutes we saw large latency spikes that were bad for user experience. After investigating, we determined the spikes were due to Go core features, its memory model, and garbage collector GC. Why did Go not meet our performance targets? To explain why Go wasn't meeting our performance targets, we first need to discuss the data structures, scale, access patterns, and architecture of the system of the service. Shit, that's cool. The data structure we use to store read state information is conveniently called read state. Discord has billions of read states. There is one read state per user per channel. Shit, per user per channel. So from a specific channel, how many messages has this user read and how many messages they haven't read. Okay, each read state has several counters that need to be updated automatically and often set to 0 after they have read everything. For example, one of the counters is how many at mentions you have in a channel. Okay, so read state, there is a read state data structure for per user per channel basis, and it has a bunch of counters, and one of the counters is like how many times you have been mentioned. Okay, which is represented by the number in red in Discord channels. Barebone Docker was implemented in Go share, so you can try making it right now. You'll know just saying. Right now, you know just saying. Yes, I will make Docker. Load. It is automatically, not auto. Atomically. You changed the whole meaning. Shit. Ah. Each read state has several counters that need to be updated atomically and often reset to 0. Atomically would mean that they need to be changed individually, I guess. Atomically. Huh? Relu. Uh, I was thinking about something. Uh, First, okay, this atomically. Yes, Docker. Uh, GitHub.com, Codecrafters. There is Docker. Let's go. We can create Docker in Go, or Python or Shell. We can create a Docker in Shell if we want to. Or there is a video about Docker in Go. Shit, 42 minutes. 42 is the answer to the whole universe. Go to references. Should that looks nice. Bocker is also something we can create in Go. Shit, this is in Shell. Yes, in Shell we can create Docker in Shell. And why does he look French? He's from UK. Peter Wilmot. Okay. Atomically. Yeah, Docker have more features, and I'm not dunking on Docker interface. In fact, I'm taking inspiration from it for my use case. And OJ, a full-blown Docker's daemon, and feature is not needed. Yes, bro, just doing whatever is required. Okay, so you made Docker for OJ. That is cool. I don't know. I should default nature, instinct. Okay, atomically. In order to get quick atomic counter update. In order to get quick atomic, again atomically, counter updates. Sure. What are atomic updates? Atomic updates are operations that are indivisible. Atomic updates are operations that are okay, the same thing, indivisible, and are performed entirely or not at all. Okay, does that make sense? Either we update the whole thing or we don't update anything in it at all, ensuring that a system's state is never left in an inconsistent or corrupted condition. Okay, this is crucial in concurrent programming and databases to prevent race conditions and partial updates. For example, in a banking transition, makes sense. Makes sense. In banking, the part where balance is reduced from the sender's account and balance is increased on the receiver's account has to be an atomic update. Okay, shared, and this also makes sense. So that I guess the server would know that this guy has read this message and also the person would know, the read state of the person would know that this user, my master, has read all of these mentions or stuff. That is cool, like atomic. Hello. When will you restart the QEMU streams? Uh, I guess not yet, but I can run my QEMU right now. VM boot, but I messed up. I messed it up. This is going to take like quite a bit of time to boot up. Yes, and now it takes like 10 to 15 seconds because the original image that I was working on was of 10 GBs, and then I installed and I was building with a friend Hyperland on this thing, and that required more space, so we had to increase the size of the disk, for which we used QEMU's file utility or some software to increase the size of the disk, and then we had to go boot into the virtual machine and tell using fdisk. We did some things, I don't remember exactly, but we told the operating system that there is now new more memory you can use, and like yeah, so but it's still it, I guess it does not natively know that there is more memory, and yeah, it waits for something to happen and this just takes time to boot up. QEMU is nice, by the way. Ah, and shit, by this guy, Fabrice Ballard. Why does he have his painting like this? That is crazy. And this is his website. Yeah, yeah, he is not very good at CSS. He wrote Tiny C compiler, TCC. He made Q Emacs, Quick Emacs. He made FFmpeg. He made FFmpeg. He made QEMU, and he's up. He has been up to some things. And this is CSS skills. Ballard.org. Fabrice Ballard, born in 1972. Shit, 1972. Godfather came out in 1972. And yes, we are in. Shit, what was the password? Yes, we are in the virtual machine now. And yes, Debian Hyperland. This is running Debian right now in QEMU. It's the best if you want just quick hack into C compiler and C trying out different things. Share like modular C compiler where we can change meanings of symbols or stuff. Yeah, this is just it. It might be shut down instead of power off. Yo, reboot, power down. Okay, back to this. In order to get quick atomic updates, each read state server, quick atomic. Cool, atomic. Now we know the meaning of atomic. Each read states server has a least recently used cache. Least recently used cache. Read state. Each server. Okay, read state server. Okay, so read states have their own server in which they are stored. Make that would make sense because there are a lot of people and read states are per channel, per channel, not even server, per channel, per user basis. That is crazy. So yeah, I guess it would make sense for read state to have its own server and everything there. There are millions of users in each cache. There are tens of, so they have their own Redis. I guess this cache would be in memory. So practically they have their own Redis. There are millions of users in each cache. There are tens of millions of read states in each cache. There are hundreds of thousands of cache updates per second, and all of them are in sync, kind of like, because atomic. Hello. I was wanting to add the ability to include files over HTTP FTP. Lol, imagine how fun it would be, just like how you can use JSON and such over HTTPs. Wait, we do use, okay, search over HTTPs and read and parse it like that. I was planning of using TCC for that. Wait, why would the compiler which you are using to compile your C code matter in what you are writing in your C code? I mean, it would matter, but using, what would be the benefit of using TCC instead of GCC? And also, this is how things happen. Uh, for downloading files, we don't use FTP now. We do use HTTPS, and that is crazy. Somehow we use HTTPS. It mostly we use for file transfer. Shit, we do use this. FTP is the most classic common protocol, and most secure protocols like this HTTPS are often preferred for sensitive data, while FTP is still widely used, particularly for web development and less sensitive data secure. So for secure data, we use HTTPS. I heard somewhere that we use more HTTP for file transfer than FTP. That is kind of crazy. Do we use more HTTP, HTTPS or FTP for data transfer? If you're talking about modern real world uses, it is not even a competition anymore. Shared. If HTTPS absolutely dominates FTPS, FTP is basically a fossil. Shit. When we break it down without things, security, we get security. FTP sends everything in plain literal text, username, passwords, and everything. HTTPS encrypts and everything that comes with the transport layer security. Firewall friendly. FTPS requires weird port gymnastics, active passive modes. Firewall hates that. Port 433. Okay, so FTP doesn't have its own port. Already expects traffic on 443. Browser native support. Yeah, we can, yeah, browser natively have embedding for HTTPS. So we use HTTPS for file transfers, and that is cool. Back to the memory management article. We have, that is like 10% of the way. Okay, we have cache, in memory cache, which is being updated like millions of times per second. For persistence, we back the cache with Cassandra database cluster. Okay, Cassandra is a database cluster, yes. On cache key eviction, we commit your read states to database. Cache key eviction. Okay, we also schedule a database commit for 30 seconds in the future whenever a read state is updated. There are tens of thousands of database writes per second. Okay, so most of the things happen on memory, but they have conditions, and at those times they store the read states in database. Okay, in the picture below you can see the response time and system CPU for a peak sample time frame for the Go service. As you might notice, there are latency and CPU spikes roughly every 2 minutes. Uh-huh. Yep. What is called sorting? So why 2 minute spikes in Go on each cache key eviction? Memory is not immediately freed. Cache key eviction. Cache key eviction. Should cache key eviction seems like a general concept, not something Discord came up with. The process of removing specific data entries keys from a cache to free up space. Okay, whenever we remove some data from the cache, we call it cache key eviction. And at those times, data is stored in the database. On cache key eviction, we commit your read states to database. That makes sense. On each cache key eviction, memory is not immediately freed. Instead, the garbage collector runs every so often to find any memory that has not referenced, that has no reference, and then freeze it. Okay, now we are at like the second layer of how things happen. There was first of all the analyzer, static analyzer, escape analyzer. Escape analyzer sees based on the scope of a variable based on its size. The escape analyzer tells the compiler whether the current data that we are using, it should go on the stack or on the heap. And yeah, so if the data is on the stack, normally when we return a function, the stack frame gets freed automatically. We don't have to do anything. But for the heap things, whenever we return from a function or explicitly free something on the heap, the memory is not freed immediately. The garbage collector will come and free the memory later on, whenever it comes. Okay. In other words, instead of freeing immediately after the memory is out of use, memory hangs out for a bit until the garbage collector can determine if it is truly out of use. During garbage collection, Go has to do a lot of work to determine what memory is free, which can also slow the program down. Makes sense. These latency spikes definitely smelled like garbage collection performance impact. We had written the Go code very efficiently and had very few allocations. We were not creating a lot of garbage. Okay, after digging through the Go source code, we learned that Go will force a garbage collection run every 2 minutes at minimum. Shit, this is a clickable link which goes to a Go documentation, I suppose. No, shit, that is crazy. That is actually crazy, the type of performance that they are trying to do. The Discord developers went through the source code of Go source code. They literally went through the source code of Go. Shit. Force period is the maximum time in nanoseconds between garbage collection. If we go, if we go this long without a garbage collection, one is forced to run. This is the variable for testing purposes. It normally doesn't change. Shit. In 64. Shit. Go is written in Go. Shit. This whole thing is a Go file. So Go is written in Go. That is a recursion. Bootstrapping. Huh. Shit. Okay, you were saying quite a bit. Something like include this header. Wait, huh? Shit, you're trying to make. Okay, my camera is not working. That is kind of cool. Let me fix it. Yeah, working. Cool. And Because the handling of include files are defined in the compiler itself, not the C source code. Yes, and I don't have enough courage to change Clang or GCC. Why misunderstood whole thing? Oh shit. Okay, so I guess Discord was okay. Something like this. Because the handling of include header files is done at the compile time source code, not the C source code. I don't in the pre-compilation step, and I don't have enough courage to change Clang or GCC. Well, okay, okay, shit, okay, okay, okay. So if there is some header file in the internet, it will be included like we do in JavaScript. So that is cool. That is actually cool. And you are making your compiler for that. That's cool. Pre-compilation. Discord was using Redis earlier, but it got so slow that they started burning money. So then they shifted to something else. Afai. Same happened with Mongo, and they had to shift to something else. Then to Cassandra. Look, now I can't even explain because I used HTTPS like URL, which wasn't even URL. Shit. Moderation is crazy. And it's called Shopify. And one more such company was there. I can't remember. They have some of the best design engineering articles. Huh. It's called Shopify. Design engineering articles. This is cool. Like they went through the Go source code. And Go is written in Go. That is like bootstrapping. Should we can make some contribution to this thing. Who is the top person? Should go Cambridge. Russ Cox, Brian Cox, or Rust Cole, or Russ shit. The guy who created Silk Road website. Uh, Ross. His name is not Russ. His name is Ross. Ross Ulbricht. And where is their parser? API libtime is source code. They must have a parser or something. P main.go. Okay, okay, not yet, not yet. Okay, moving back. So they went through the Go source code and found out that the garbage collector will run every 2 minutes at minimum. Go source code is honestly pretty simple to read. Can't say the same about making changes though. Shit. I have not read any source code like ever for anything, and that would be a good experience. Yeah, I'll start doing that. We figured we could tune the garbage collector to happen more often in order to prevent large spikes. Okay, so we implemented an endpoint on the service to change the garbage collector GC percent on the fly. Unfortunately, no matter how we configured the GC percent, nothing changed. How could that be? It turns out it was because we were not allocating memory quickly enough for it to force garbage collection to happen more often. We kept digging, and learned that spikes were huge, not because of a massive amount of ready to free memory, but because the garbage collector needed to scan the entire LRU cache, least recently used. So where did LRU? Least recently used cache. Okay, LRU cache in order to determine if the memory was truly free from references. Thus, we figured a smaller LRU cache would be faster because the garbage collector would know would have less to scan, so we added another setting to the service to change the size of the LRU cache and changed the architecture to have many partitioned LRU caches per server. We were right. With the LRU cache smaller, garbage collector resulted in smaller spikes. Unfortunately, the trade of making the LRU cache smaller resulted in higher 99% 99th latency times. Higher 99th latency times. This is because if the cache is smaller, it is less likely for a user's read state to be in the cache. Makes sense. If it is not in the cache, then we have to do a database load. After a significant amount of load, testing different cache capacities, we found a setting that seemed okay, not completely satisfied, but satisfied enough with bigger fish to fry. We left the service running like this for quite some time. During that time, we were seeing more and more success with Rust in other parts of Discord, and we collectively decided we wanted to create the frameworks and libraries needed to build new services fully in Rust. This service was a great candidate to port to Rust since it was small and self-contained. But we also hoped that Rust would fix these latency spikes, so we took on the task of porting read states to Rust, hoping to prove out Rust as a service language and improve the user experience. That is cool, and the fact that all of this is kind of making sense is even cooler. Okay, they have read states and they were facing difficulty because of the garbage collector was messing up go source code. But yeah, reading and understanding it is pretty easy, very easily understandable. I guess we can, yeah, I'll do some digging. Do that. You can even view all of the standard library, its implementation. Shit, I want to see some things. I wanted to see the implementation of C things, of things in C, but C++ library, but I was unable to find them. Okay, they have a pinned project named go lib time hg fips webassembly time hg gore possum. Time is something, time has some source. FMT shit. Scan print. What does print do? It has package FMT is this, and it has constants. Okay, states in formatter, stringer, go string. PP is a data structure. New printer, new scanner would also be something. And let's see. Okay, shit, we do have append. We see append, right? And we have buffer. Buffer is a data structure symbol type buffer. Okay, for referring to a array of bytes, or this is a slice of bytes, we will call a slice of bytes a buffer. Printf, printf, that is the literal thing. Okay, return OS standard out if printf. Write to IO writer. This takes in a writer where to write, and the format called string, and a type anything, and a. Okay, any number of arguments. This returns an integer and an error. P gets a new printer. Do printf with this format these things. So yeah, format this stuff. Okay, and n and error. Write to this writer w dot write the buffer in p, and then p dot free, and then return. That is cool. That is cool. We literally have stuff here. That is actually cool. Open source. Okay, and memory management in Rust. Rust is blazingly fast and memory efficient with no runtime or garbage collector. With no runtime, yes, or garbage collector, it can power performance critical services, run on embedded systems, and easily integrate with other languages. Rust API, yeah. BPI, binary ABI, application binary interface. Rust does not have garbage collection, so we figured it would not have the same latency spikes Go had. Rust uses a relatively unique memory management approach that incorporates the idea of memory ownership. Basically, Rust keeps track of who can read and write to memory. It knows when the program is using memory and immediately frees the memory once it is no longer needed. It enforces memory rules at compile time, making it virtually impossible to have runtime memory bugs. Virtually, you do not need to manually keep track of memory. The compiler takes care of it. So in the Rust version of read states service, when a user's read state is evicted from the LRU cache, it is immediately freed from memory. The read state memory does not sit around waiting for the garbage collector to collect it, because there is no garbage collector, and Rust knows immediately when the memory goes out of scope and is not needed. Rust knows it is no longer in use and frees it immediately. There is no runtime process to determine if it should be freed. Yes, no runtime overhead. Async Rust. But there was a problem with the Rust ecosystem. At the time the service was re-implemented, Rust stable did not have a very good story for asynchronous Rust. For a networked service, asynchronous programming is a requirement. There were a few community libraries that enabled asynchronous Rust, but they required a significant amount of ceremony, and the error messages were extremely obtuse. Unfortunately, the Rust team was hard at work. Fortunately, the Rust team was hard at work on making asynchronous programming easy, and it was available in the unstable nightly channel of Rust. Okay, they had asynchronous Rust, which was something that they had to use. Discord has never been afraid of embracing new technologies that look promising. For example, we were early adopters of Elixir, React, React Native, and Scala. I don't know Scala, and Elixir is a language. If a piece of technology is promising and gives us an advantage, we do not mind dealing with the inherent difficulties and instability of the bleeding edge. This is one of the ways we have quickly reached 250 million plus users with less than 50 engineers. That is crazy. They have less than 50 engineers. When did Einstein die? Elixir, uh, programming language created. 2011. Shit, this is new. Newer than Rust. Elixir, programming language. Implementation of C functions seems a bit little too tough. I couldn't even think about CPP. Yeah, CPP. Yeah, I was looking for like how are these things happening under the hood, but I was unable to find it. And also, the error messages are too obscure or too obtuse to understand. Shit. Yeah, this is Elixir. Here is a peak. Shit, peak Elixir experience. Spawn link. Yeah, we are not doing Elixir right now. Back to this. Okay, embracing new technologies. Embracing the new async features in Rust nightly is another example of our willingness to embrace new promising technology. As an engineering team, we decided it was worth using nightly Rust, and we committed to running on nightly until async was fully supported on stable. Together, we dealt with any problems that arose, and at this point, Rust stable supports asynchronous. The bit paid off. Gambling, implementation, load, testing, and launch. The actual rewrite was fairly straightforward. It started as a rough translation, then we slimmed it down where it made sense. For instance, Rust has a great type system with extensive supports for generics, and enums are crazy in Rust. So we could throw out Go code that existed simply due to lack of generics. Also, Rust's memory model is able to reason about memory safety across threads. So we were able to throw away some of the manual cross Go routine memory protection that we required in Go. When we started load testing, we were instantly pleased with the results. The latency of the Rust version was just as good as Go's and had no latency spikes. Okay, that is cool. Remarkably, we had only put very basic thought into optimization as the Rust version was written. Even with just basic optimization, Rust was able to outperform the hyper hand tuned Go version. This is a huge testament to how easy it is to write efficient programs with Rust compared to deep dive we had to do with Go. Bro was literally going through Go source code, but we weren't satisfied with simple matching Go's performance. After a bit of profiling and performance optimizations, we were able to beat Go on every single performance metric. Latency, CPU, and memory were all better in the Rust version. The Rust performance optimizations included changing a B tree map instead of a changing to a B tree balanced tree map instead of a hash map. Shit, hash maps are not very good. They are slow. B trees are actually pretty cool. In the LRU cache to optimize memory usage. Memory to optimize. They switched to B trees instead of maps for memory. I would say, with my limited understanding, that switching from hash maps to B trees would be a performance gain instead of being a memory gain. Abstraction and OP, I feel like, because the error messages traces back to every class and function which inherits or overrides or anything. Okay, so like it goes through the whole stack. C errors are good. Rust errors are amazing. They literally tell you where the mistake is, on which line you messed up. I'm more of a C guy. Shit, I mean, okay, that is also cool. C. Shit, how can, like, I've not written much stuff in C. Most of my stuff is in C++. It would be a nightmare to do memory allocation on the heap, get a dynamic sized array in C. Like, you have it in C++ by default, but you would have to create something in C or use some library to get a dynamic size array, and then make sure you are not messing up the memory. Okay, swapping out the initial metric library for one that used modern Rust concurrency, reducing the number of memory copies we were doing. Okay, swapping out the initial metric library for one that used modern Rust concurrency. Okay, reducing the number of memory copies we were doing. Because by default in Rust we use a move operator instead of a copy operator. Satisfied, we decided to roll out the service. The launch was fairly seamless because load tested we load tested but put it out a single canary node. Found a few edge cases that were missing and fixed them. Soon after that, we rolled it out to the entire fleet. Blue are the results. Go is purple, Rust is blue. Go is purple and Rust is blue. Shit. Maximum shit here. Rust is amazing. here Rust is, of course, like amazing. The peaks are higher than Rust's average. But okay, this thing, I guess, because yeah, the memory freeing takes up time. The memory freeing takes up time. So this uh, high base value in this graph, I guess that makes sense because memory freeing. At the times when the CPU usage is low in Go, there is no memory being freed. So yeah, mostly I don't need dynamic arrays. I have enough RAM. Shit. So even if you need an array that would take like 10 MBs or 10 elements, you would make an array of size 1 billion or something. So I allocate a bit more. Shit. That I think is a cool thing. Shit, I have not thought of this method, but that does make sense. Yeah, I guess I might be able to use it as some places. But yeah, this is the first time I'm hearing of this trick. After a while, I like my peace of mind more than syntactical sugar of the language. Bro wants to have a nice sleep at night. Raising the cache capacity. Raising the cache capacity. After the service ran successfully for a few days, we decided it was time to re-raise the LRU cache capacity. In Go version, as mentioned above, raising the cache cap of the LRU resulted in longer garbage collection. We no longer had to deal with garbage collection, so we found we could raise the cap of cache and get even better performance. We increased the memory capacity for boxes, optimized the data structure to use even less memory for fun. Okay, so they updated the read state data structure and also the cache in which it was being stored and increased the cache capacity to 8 million read states. I think it was a couple of hundred thousands before. Now it is around 8 million, and before there are millions of users and there are tens of millions of read states in each cache. Okay, there were tens of millions of read states in each cache, then they reduced the size and now they re-increased the size to 8 million. The result below speak for themselves, chess speaks for itself. Notice the average time is now measured in milliseconds. Max match. Okay, they do not have comparison with Go, but that is cool. Milliseconds. Yo. Closing thoughts. SDK, System Development Kit. Finally, another great thing about Rust is that it has quickly evolved. It has a quickly evolving ecosystem. Recently, Tokyo had a CSV. I'll be back soon. Yo. Okay. Released version 0.02 and we upgraded and it gave us CPU benefits for free. Below you can see the CPU is consistently getting lower starting around the 16th. Yeah, around the 16th the peaks are lower. Closing thoughts. Let's see, at this point Discord is using Rust in many places across its software stack. We use it for the same SDK, video capture and encoding for Go Live Elixir, NIFs, several backend services and more. When starting a new project or software component, we consider using Rust. Of course, we only use it where it makes sense. Along with the performance, Rust has many advantages for an engineering team. For example, its type safety and borrow checker makes it very easy to refactor code as product requirements change or new learnings about the language are discovered. Also, the ecosystem and tooling are excellent and have a significant amount of momentum behind them. If you make it this far, if you made it this far, you are probably newly excited about Rust or have been excited for quite some time. If you want to work on interesting problems using Rust professionally, you should consider working here at Discord. Shit, they are giving us a working opportunity. Also, fun fact, the Rust team uses Discord to coordinate. So that is cyclic dependency. There is even a very helpful Rust community server that you can find us chatting in from time to time. Think I am a part of the Rust server. Go version, this edit graph. Okay, shit, we can work at Discord if we want to. That was a nice article. Functions which take variable arguments. Yes, back to this. There are some stuff left in this spread operator. Let's now we can go through this go memory model, or let's first complete the boot.dev thing. Yeah, and we were able to understand a few things from the Discord article, that the garbage collector runs at minimum of every 2 minutes. And yes, and when we free stuff on the heap, it doesn't get freed immediately, it gets freed when the garbage collector runs. And if the size of the cache which we are storing stuff, if that is big or small, whatever, garbage collector goes through the whole thing to determine if there are what are the things that we are not using or we were using or whatever it is. Sleep schedule is cooked. Shit. Bro woke up just now, I guess. Or is going to sleep now. I don't know. Go memory model. Yeah, let's go through this. Variadic, variadic functions which can take different sizes of arguments. And we have written some stuff here. Data will be given as a slice. That is cool. Yep. String, slice of string. The familiar print are variadic. That makes sense. We can provide in anything at any size. And then there is the spread operator. If you have a thing, it can be spread. Okay, the spread operator allows us to pass a slice into a variadic function. The spread operator consists of three dots following the slice in the function call. So I guess it couldn't convert argument to string. That is completely fine. Let's say we have array which is in array which has two things, and this is an array, not a slice. This is an legit array which has two numbers, 37 and 42. And then fmt dot println, this works, and then this does not work. Cannot use array variable of type 2 as any variable. Okay, we can only use this for slices. We cannot even use this for slices. Variable of x as any value in argument. Huh. Okay. This does not work. This does not work. This does not work. Compiler cannot use array type of this as any value in argument fmt. Why? Can we not use this here? 1 to 3, it does take print screens. If you have a function which my func it takes x, which is a integer thing, and fmt dot print ln x, and here my function cannot use this in non-adiabatic function. Okay, say any amount of integers or any amount of any. Okay, now we have the same problem here. Any, we can have any amount of any. We can spread x here without problem, but we cannot spread array here somehow. Dot append length last. Append length and last. Why can we not do this? Array is integer 1, 2, 3 is giving error and go. This is giving error and go. You close, the problem is just how you declare the slice. This thing is valid go. If this accepts that many arguments of that type, and guess what, it does. So the real issue is probably your variable is not actually a slice, even though you think it is. The actual correct version would be something like this, which is the exact same thing. This compiles just fine. No, it does not compile just fine. What causes the error in real life? This is an array, not a slice. We cannot expand arrays, it seems. This is the error, and let's see. Okay, all right, now we have the actual diagnostic. This error does not come from the Go compiler. This error comes from your LSP static analyzer, likely Go LSP misanalyzing your code. Go compiler itself accepts your code perfectly. Let me show you why. Actual compiler behavior, this compiles. Let's see if this compiles or not. So they are saying the LSP is messed up. No, LSP is fine. Why LSP complains? This thing is not equal to this. Update go fix LSP. No, it is not the LSP. The compiler itself is complaining. Whatever the problem was, we can use a spread. Okay, nice. Append, the built-in append function takes in a slice and the items of the type of slice. Which one? Shit, we can give multiple items to append. That is nice. May not go. Okay, and append to array 1, 2, 3. All this. And v dot println Go run this current thing, and cool, we can append multiple things. That is cool. In the underlying array, if the underlying array is not large enough, append will create a new array. Let's mm, array to spread the array to, and too many arguments in the call to append. After the append, we cannot expand an array, we can expand a slice. Okay, go run this current file and does run. Notice the append is a VDAtic function manually or through expansion. Range, yes. Go provides syntactic sugar to iterate easily over elements of a slice. Range function. Range, and we give it a slice and the first thing and the second thing. Okay, the element is a copy of the value at the index. Yes, we did discover that firsthand. So fruits is a slice, range fruits, index and fruit. Print this assignment, whatever it is, and then slice of slices. Slice can hold other slices. So this is a slice of slice. Rows, append a new slice, this thing, and then we can print it. That is nice. Let's write a pattern. We'll say grid equals slice of slice int declared and not used, does not matter. Okay, yes, it is empty right now. Grid equals append to grid a new slice 1 2 3 2 3 4, or let's use 1 1 1 1 1 5 by 5. Yeah, let's make this 5 by 5. Okay, and this is what we should see. Simply dot print ln the grid. Go run this thing, and it comes on the same line. That is not very cool. Would look like this. We will have to write a custom function if we want to give spaces between each individual smaller slice. For we don't need the index, we just need the slice slice and range grid open dot print line slice. Print the slice, and yeah, cool. And go run this thing, and yo, we have a box that is pretty cool, and it is also working. Moving on to the next thing, tricky slices. The append function changes the underlying array of its parameter and returns a new slice. This means that using append on any other than itself is usually a bad idea because the original one also changes. To do this, other slice and some slice. Take a look at these head scratchers. We have slice A, length of A 3 3. Okay, cool. And then we append 4 to A and make it equal to B. So B print appending this, and then print length B would be 0004. Makes sense. And the address of B would be address of the first element, which is something like this. And then we append to A5. We will have 0005. No, we have 0005. Append. Appending 5 to C from A. Address of C is this. Something. Print ln of this. Works as expected. Something is fishy. Okay, here we had A. So take a look at this. Append changes the underlying array of its parameter and returns a new slice. A new slice is returned. Okay. With slices A, B, and C, 4 and 5 seem to append. This makes sense because A does not have enough storage. So the append function creates a new array and returns the new one. Makes sense, and does not change the original A array because it does not have enough space to append new stuff. We can check this by the memory address. Okay, and then here the capacity is higher, right? 3 and A, and we append 4, so J would become 0004, and J would become 0004, and I think A and J would point to the same thing. Address of J is this 0004, and G would be 00045. No, G is not 000445. Yes, they are pointing to the same thing, but A's size, I's size is still 3. So the new thing added, appended on I will be added at the same location that 4 was added because I's size is still 3. So at the fourth location. And I and J are pointing to the same thing. Yeah, that makes sense. My slice is this, and my slice equals append to my slice. 4. This also works. Against avoid bugs like this. Yeah, we also always assign to the same thing. Why is 5 the final value in the last of J? Because the size of I is still 3, and that overwrites the location where 4 was written, and we didn't update I. J and I go point to the same underlying array, so G's append. Yes, that is the correct answer. Go team beat trolling. No, because append only works properly when the number of elements. No, because 5 was appended to I to create J. No, the first one. Why doesn't the bug regarding slices J and G in example 2 occur in example 1 as well? Because in example 1 we are not writing in the A array itself because A does not have enough space. We are returning, append function is returning a new array, and yeah, so B and A are not pointing to the same underlying array. The array's capacity is exceeded, so new underlying array is allocated. Yes, that is the answer. This array in example 1 had a larger starting. Nope, because there are fewer elements and go runtime can't handle that. No, first one is the correct answer. And tricky slices, the same thing. How can you best avoid these kinds of bugs? By not assigning the return value of append to some other variable, into some other slice. Don't use the append function, use the append function. Always assign the result of the append function to a new slice. No, always assign the result of the append function back to the same slice. Yes, C. Send your message filter that I guess Mrs. Filter text you. Yeah, that is something related to their course. Password string, that is also something related to their course. Mrs. Dagger, that is fine. Okay, cool. And now we are on to maps. I guess we won't be doing maps today. We will be reading. It has been just 2 hours and 44 minutes. This seems longer than that. Okay, we have learned quite a few stuff. Escape analyzer in Go, and the memory management, that is the Rust. Yeah, not Rust. The garbage collector runs every so often to free memory which was read. Uh, yeah, let's close this with by going through Go memory model, this article. Yeah, let's go through this article, and that would be it. Go garbage collector. How does the garbage collector work? Yo, nope. Go memory model. Let's go through this thing. And yeah, before moving on with this, I would like to go through the washroom, and I'll be right back. We'll do this. Go memory model from 2022, 3 years ago. And garbage collector article was there is no date for garbage collection. Shit, they do not have a black background behind this. That is crazy. Or maybe because I'm using this thing, uh, dark reader, for making this dark. I guess if I turn this off, yes, now it would be, yeah, now the background is black. Makes sense. Cool. We'll go through this article and we can close other stuff. And yes, I'll be back in a minute. And I'm back. Let's go through the article. Go memory model. Go introduction. The Go memory model specifies the condition under which reads of variable in one Go routine can be guaranteed to observe values produced by writes to the same variable in different Go routines. That okay. Wait. The Go memory model specifies the conditions under which reads of a variable in one Go routine can be guaranteed to observe values produced by writes to the same variable in different Go routines. Different Go routines, like functions, different functions can communicate through through the same variable by passing values by value. Writes programs that modify data being simultaneously accessed by multiple Go routines must serialize such access. Okay, like using mutex to serialize access, protect the data with channel operations or other synchronization primitives such as those in the sync and sync atomic packages. If you must read the rest of this document to understand the behavior of your program, you are being too clever. If you must read the rest of this document to understand the behavior of your program, you are being too clever. Don't be clever. Okay, informal overview. Go approaches its memory model in much the same way as the rest of the language. Wait, so Go is the language, and we are talking about the language, and how can the language approach its memory management model? Shit, Go memory model. Okay, shit. Okay. Since Go language itself is also written in Go, so they are here talking about how the implementation of Go handles memory management, not how it is handled in the language inherently. Shit. Okay, so this is not something that we have to read. Yeah, this is not what we want. This is not what we want. This is not what we want. Um, yeah, Go dev. Shit, we went to the wrong website. Yes, we do not want to contribute to Go itself. Go, not Goodreads. We will read the article on garbage collection. Go dev, no. Go, yes. These were the Go language programming in specifications. That is not what we want. We want the user side stuff. Garbage. Yeah, a guide to the Go garbage collector. Let's read this. And yeah, that is what we want. And what we have established till now is this escape analyzer and stack and heap. And the developer doesn't need to know whether the variable is going to the stack or to the heap. Okay, introduction. This guide is intended to aid advanced Go users in better understanding. Yeah, this is my fifth day in Go. Advanced Go users in better understanding their application costs by providing insight into the Go garbage collector. It also provides guidance on how Go users may use these insights to improve their application's resource utilization. It does not assume any knowledge of garbage collection, but does assume familiarity with the Go programming language. I think we pass the criteria. The Go language takes responsibility for arranging the storage of Go values. In most cases, a Go developer need not care about where these values are stored. Why or why, if at all? In practice, however, these values often need to be stored in computer physical memory, and physical memory is a infinite resource. Because it is finite, memory must be managed carefully and recycled in order to avoid running out of it while executing a Go program. It is a job, it's the job of a Go implementation to allocate and reallocate memory as needed. Another team of automatically recycling memory is garbage collection. At a high level, a garbage collector, or GC for short, is a system that recycles memory on behalf of the application by identifying which parts of the memory are no longer needed. The Go standard toolchain provides a system library that ships with every application, and this runtime library includes the Go standard toolchain provides a system runtime library which will run at when the program runs and is included in the binary that ships with every application, and this runtime includes a garbage collector. Okay, that is cool. And now most of this thing is just me going to read this article. The rest of the stream is going to be that, and my laptop is going to die. Okay, garbage collector comes with the runtime and is shipped with every application. Note that the existence of a garbage collector as described by this guide is not guaranteed by the Go specification. Okay, so so this is implicit. This design of the garbage collector is implicit and is not guaranteed by the Go specification. Only that the underlying storage for Go values is managed by the language itself. This omission is intentional and enables the use of radically different memory management techniques. Okay, okay, that is cool. So the Go garbage collector specification is implementation defined, not specification defined. Therefore, this guide is about, okay, let that sink in. The model for the garbage collector is implementation defined, not specification defined. Okay. Therefore, this guide is about a specific implementation of the Go programming language and may not apply to other implementations. I guess we are using the Go official runtime, so this would work. Specifically, this following guide applies to the standard Go toolchain, GC, garbage collector, Go compiler, and tools. GCC Go and Go LLVM both use a very similar garbage collector implementation, so many of the same concepts apply, but details may vary. And GCC Go is a Go compiler with GCC as the backend, and Go LLVM uses LLVM as the backend. Furthermore, this is a living document and will change over time to best reflect the latest release of Go. This one is for Go 1.19. Shit. 1.12, 1.25, and this is for 1.19. Okay, where Go values live. Before we dive into the garbage collector, let's first discuss the memory that doesn't need to be managed by the garbage collector. That is the stack memory. For instance, non-pointer Go values stored in non-pointer Go values stored in local variables will likely not be managed by the Go garbage collector at all, and Go will instead arrange for memory to be allocated that is tied to lexical scoping in which it is created. In general, this is more efficient than relying on the garbage collector because Go compiler is able to predetermine when that memory may be freed and emit machine instructions that clean up. Okay, that is nice. Typically, we refer to allocating memory for Go values this way as stack allocation because the space is stored on the Go routine stack. Yes, yes, and that is what is preferred to store memory on the stack. Go values whose memory cannot be allocated this way because the Go compiler cannot determine its lifetime are set to escape to the heap. The heap can be thought of as a catch-all for memory allocation. For when Go values need to be placed somewhere, let's write a function that is going to take a lot of memory in Go. May not Go, and we will write a function that memory doesn't take in anything but returns a slice of integers and slice and yeah. Okay, my bad. here. Okay, we have our stuff which is of type int, and shit. And let's give this thing size. Uh, size. Can we give it outside like this? 1E7. Make array size. Variable of that would be the size, and let's increase it even higher than this. Or that might be too much. That might be too much. Let's decrease by 3 orders of magnitude and return here. And let's how to make the main go routine sleep. Okay, time dot sleep, time dot seconds or 2 seconds. Okay, while or for true, for true. uh, Time initially equals 0, and here we'll say 70 dot print ln print line time, then call memory. just just call it. We'll even do this, and yeah, we want. You're not using it. I guess that is okay. That is okay. We would still be using it. Okay. And then time dot sleep for 1 second. And tm plus plus. So every second we are getting quite a bit of memory. Right. Every second we are getting quite a bit of memory. What is 26 into 3? That would be 78. And we'll have a new window with what is 21 into 25? That would be 525. Okay. And that does work. Shit, but we needed a new pane, not a new window. Right, shit. Okay. 52 into 15, 750, 750, 780, 780. Split here. 94 into 55, that would be 550 minus 55 into 6, that is 300, 330, 520, 5200 minus 35,170, 5,170. Let's see if that is correct. Here, go run current file, and here beta. Shit, this is too small. Okay, let's use the activity monitor. Yo, let's go. Activity monitor and process name memory. Memory, where is the Go process? Boot.Dev, it is taking 14 GB of memory. Alright, that is great. Let's open another terminal and we can run boot btop here. What is 8 into 90? 720. Yo, hello. How are you? I am amazing. How are you? Tantai NG Tantai 1001. Okay, and btop. Let's see how much memory is boot.dev taking. 1.1 GB. That is a lot. We are intentionally creating memory leak, and the Go runtime is the Go garbage collector is not collecting the memory. The Go garbage collector is not collecting the memory because it runs once every 2 minutes at minimum, and it has only been about 38 seconds or so, 1 minute or so. Okay, shit, this is CPU time. My bad. Memory. This is memory used memory. Yes. Boot.Dev is taking the maximum number of amount of memory, 1.1 GB, and it is stuck at 1.1 GB. So I guess the garbage collector is running from time to time. So that is cool. Stop and shit. Now run beta. Where all the data is gone. Yes, it is not taking any memory anymore. The program is gone, and now everything is kind of quiet here. That is cool. And back to the article. Back to the future. And back to my old ways again. Go values whose memory cannot be allocated this way because the Go compiler cannot determine its lifetime and said to be escape to the heap can be thought of as a catch-all memory. And the code that I just ran is this simple function allocate some memory of this much integer. One integer is 4 bytes, and we are taking 4 billion bytes. How much memory is 4 billion bytes? 1 million bytes would be 1 MB. 4 billion bytes would be 4 GB. Shit, 4 gigabytes. 4, that actually is. Shit, this actually is asking for GBs. 4 GB of data. Shit, this actually is asking for 4 GB of data. That is crazy. And let's give this return type a name, and we'll say we'll return stuff and stuff. Stuff is here, and so we can call the append here. Append to stuff. Make. Append to stuff. Make. Type this much size, and spread. Does not work. No new variable on the left side. That is also true. Let's go. Missing return we can return. And stuff But this is the stuff that will be returned by default. So that is cool, some cool Go stuff. Okay, there are many reasons why a Go value might need to escape to the heap. One reason could be that its size is dynamically determined. The instance, Consider, for instance, the backing array of a slice whose initial size is determined by a value rather than a constant. By a value rather than a constant makes sense. Note that escaping to the heap must also be transitive. Transitive. If a reference to a Go value is written into another Go value that has already been determined to escape, that value must also escape. Okay, but this is in terms of reference, not by value. Transitive. If a reference to a Go value is written to another Go value, if a reference is written to another Go value that has already been determined to escape. Okay, makes sense. So this is like here stuff is going to escape. Yeah, stuff is going to escape, and if we were to do new stuff, make something, uh, make byte size, and here instead of this we were to say now new stuff will also escape. Stuff was escaping by default. Now new stuff is also escaping. That is what we have here. Uh, okay, dynamically allocated transitive Go value that has already been determined to escape. The original one will also escape. Whether a Go value escapes or not is a function of the context in which it is used and the Go compiler's escape analysis algorithm. Escape analysis. Yes, and this is implementation defined. It would be fragile and difficult to try to enumerate precisely when values escape. The algorithm itself is fairly sophisticated and changes between Go releases. For some details on how to identify which values escape and which do not, see this section now. So they are using some algorithm to determine whether some values escape to the heap or not, and depending on what the algorithm says about a value, it is allocated either on the heap or on the stack. Okay. Tracing garbage collection. Garbage collection may refer to many different methods of automatically recycling memory. For example, reference counting, counting the number of references, and when the references goes to 0 for a value, then that value is freed from the heap if it was on the heap. In the context of this document, garbage collection refers to tracing garbage collection. Tracing garbage collection, which identifies in use so-called live objects by following pointers transitively. Let's define these terms more rigorously. An object is dynamically allocated piece of memory that contains one or more Go values. An object is dynamically allocated, which means it is on the heap of memory that contains one or more Go values. Okay, something that is on the heap which has values. Okay, and then there is a pointer, which is kind of the handler. Yep, right. And pointer, a memory address that references any value within an object. A memory address that references any value within an object. Yes, yes. So this is the actual data, and this is the handler of the data through which we can access the data, which is inside the object. This naturally includes Go values of the form pointer to type T, but also includes parts of built-in Go values. Strings, slices, channels, maps, and interface values all contain memory addresses that the garbage collector must trace. Okay, to other objects and pointers to other objects form the object graph. We have a pointer which acts as an edge, and that pointer could be stored inside an object pointing to another object, which internally could have another pointer pointing to another object. So yeah, we have a graph, a tree, not a tree specifically, but a graph. To identify live memory, the GC garbage collector walks the object graph starting at the program's root pointers that identify objects that are defined in use by the program. Two examples of root are local variables and global variables. Okay, there are multiple roots. The garbage collector goes through this object tree. Okay, the process of walking the object graph is referred to as scanning. Another phase you might see in the Go documentation is whether an object is reachable, which just means that the object can be reached by the scanning process. Note also that with one exception, once memory becomes unreachable, it stays unreachable. With one exception, I guess when you have two pointers pointing to two different objects, you can take their XOR, you can take XOR of them and store that in one pointer and override the pointer's original value. Like I have one pointer P1 pointing to some object O1 in the heap, and I have another pointer P2 pointing to some object O2 on the heap. Both of these are on the heap HP. And what we can do is right now it is has the address of O1. This has the address of O2. What we can do is instead of storing the address of O2 in this one, we can say this is address of O2 XOR address of O1. So at this point, and then also typecast this pointer to be an integer. So P is now an integer, and that integer value is not pointing to any valuable memory location. It is just some chunk, some number. So from the garbage collector's point of view, this object is not reachable, but we can still reach it if we change the type of this P2 from an integer back to a pointer, and also make this thing, this value P2, and do P2 equals P2 XOR with P1. Take its XOR again with P1 and make this a pointer. So we will get back our pointer to the second object, and cool. We have now reached an object which became unreachable for a short duration of time. This basic algorithm is common to all tracking. Okay, so the garbage collector does a thing called scanning, and if there are objects which are unreachable, there are some objects which are reachable, some which are unreachable from the graph tree object tree. This basic algorithm is common to all tracing GC garbage collectors, where tracing GCs differ is what they do once they discover memory is live. Ghost GC uses the mark sweep technique, which means that in order to keep track of its progress, the garbage collector also marks the values it encounters as live. Once tracing is complete, the Go collector walks over all memory in the heap and makes all memory that is not marked available for allocation. This process is called sweeping. Okay, object graph, scanning, unreachable things, marking, mark sweeping, and then sweeping. The one alternative technique you may be familiar with is to actually move the object to a new part of the memory and leave behind a forwarding pointer that is later used to update all the application's pointers. We call a GC that moves objects moving GC. Go has a non-moving GC. Okay. How does this thing work? Yeah, we have a few things. We have some things called pointers, and we have objects. Objects, objects, yes, are on heap. Objects are on heap. Pointers point to objects. And we have something like this. Pointers point to objects. That is cool. And yeah, objects might internally even contain pointers. Objects might contain pointers to other objects. The objects might themselves contain pointers to other objects, and we have pointers. And this makes an object graph. This makes an object graph. And let's make the graph. Let's make a few roots. We have a few roots, and yeah, let's make the connections. This is another root. Cool. They can be connected in any which way. Yeah, cool. And the labels says should do this. This is a root. Okay. This is also a root. And this makes an object graph. We have an object graph. Makes sense. We have pointers pointing to objects, and those objects might themselves have pointers which are pointing to other objects, and therefore we have roots. And let's say roots can be global. Examples of root objects or pointers, global scope, and stack frame. Cool. And yep, then the garbage collector starts its work. Garbage collector. What does the garbage collector do then? Garbage collector starts moving from the root. Starts moving from the root called scanning. This process is called scanning. The garbage collector starts moving from the root, and this process is called scanning. And whenever it encounters some new object, the object is marked. The object is marked. after scanning the whole graph happens after spanning the whole graph. GC goes through the through all the objects located on the heap and sets up the unmarked objects as allocable allocable allocatable as allocatable. These objects are called untreatable. And I guess that is cool. That is cool. And that is good enough. That is good enough. And that would also be the end of today's stream. I guess I cannot go through the whole remaining article, but we got the main part correct, I guess. The garbage collector does some garbage collecting by going through the object graph, and it keeps marking all the objects that it is seeing and then goes through all the objects which are allocated on the heap. And if sees an object which is not marked, then it means that that object is unreachable from the object graph and frees the memory that the object is taking. You have go GC and then understanding costs. Yeah, cost analysis and stuff. Yeah, that would be it. Hello, everyone. You just hopped in to the stream, and here is the gentle reminder to hydrate and take care of yourself. Thank you. Yep. You also drink some water. And that would be it for today. We went through garbage collection and in Go, and that is cool. This Yes, today we learned quite a few new things. That there is this thing called escape analyzer, which decides whether to put its stuff on the stack or on the heap in Go, and then how the garbage collector works in Go. That is cool, and also the fact that the developer mm, like doesn't specifically has to know where the values are going, either on the stack or on the heap. And we also read the Discord article about why they were changing their model, a bit of their code base from Go to Rust, and what were the issues related. And yep, that would be it for today. And thank you for being here. Bye. Your camera is not lagging. That is cool.